Okay, so we're gonna start the last session of the day with Lucas Einig, who's gonna tell us about quantifying the information content of spectral traces for interstellar medium studies.
That's better. Okay, so I'll make my presentation about quantifying the information content from astrophysical observation. It's a work that I've done within the RMB consortium, especially with Pierre Paluche, once again. So the goal of this presentation will be to be able to derive, so to formalize what is the statistical dependencies between physical parameters and observations. It's it's a question which is like quite imprecise. So we'll try to define properly what it is. What are the statistical dependencies? We'll see whether the correlation coefficient is suited to capture the relationships, and to be able to handle variables that are in different scales, for instance, like G0, which is in log scale, contrary to other observations. And we'll try also to distinct the relationships between physical regimes, so whole program. So we'll try to define a rigorous framework, which will be the information theory framework. A convenience statistics will be the mutual information, we'll see it later. And to properly define what is a statistical relationships within the information theory framework. So first, we'll try to define it properly. It will be the first two parts. After that, I will present the paper I published with Pierre, which is about the identification of the most informative observation using ISM simulations. And after that, I will quickly present other approach that use information theory, but in a completely other use for a completely other use case, which is the denoising of position velocity cube. Okay. So first, we'll model the observation and the physical parameters at full random variables. So it means that when you have a map, you can draw samples from random variables, and that will be your observations, or something like that, for instance, the observation of physical parameters. So here they are just realization, just observation of a random variable. In our case, we will just completely disregard the spatial information, which means that the first image and the second image for us will be completely the same. There will just be the histogram, which are the empirical distribution that will matter. The spatial information is interesting in astrophysics, of course. In our case, we are not interested by this, just by the relationships between the pixels from different observation or quantities. And it doesn't matter whether the neighborhood of this pixel has a spatial values. It will just complicate the analysis. So in our case, we will denote theta physical parameters, and with a lowercase letter, the realization of these variables, and same with y for the emission life, what would be the observations. So if we observe an emission live several times, we'll have several values, especially due to noise. So in practice, we know that, and what we want to do is to maybe observe several times, observe several objects in order to derive properties of the random variables. So this is something which is quite usual for you. In order to quantify the informativity of observations, I will take this example. This is a joint distribution of theta and y. So theta is the physical parameters, for instance, G0 or the visual extinction, and y is just an observation of a line, 12CO, for instance. And so you have a correlations. On the second graph, you will see here a curve, which is a log normal distributions of the theta parameters. This is the prior distribution of theta we don't know any observations. So without knowing anything, you know that empirically theta has this shape. If you observe a value of y, you will have a new distribution of theta, which is more likely to be in this region of the distributions. So you will have a gain of information thanks to your observations. If the observations is different, you will have another curve, etc., etc. When we will talk about gain of information, it will depend on the observations. For instance, the blue curve is more tight than the red curve. And so we have more gain of information here than here. In statistics, in information theory, when we talk about gain of information, this is always in average. So we will average and the distribution of all the possible observations in order to compute the average gain of informations. For another distribution like this, we'll have this kind of curve. So it's more complicated to derive a value of theta thanks to observations because this is the variable are more independent to each other. So in order to do that, we have several statistics that we can use. The correlation coefficient is a good candidate, something that we use a lot in astrophysics. The problem is that it will struggle in a lot of cases to capture statistical relationships. So this is not a good candidate, especially if we have several observations at the same time. Generally in astrophysics, we are computing in ISM, we are computing line ratios just because we don't know how to compute correctly the linear correlation with three quantities. And for instance, in the monopoly code, we have this kind of map of parameters. And so you can see that computing something linear here is a bit complicated. We have other statistics, canonical correlations, Spearman correlations, but they are not good candidates for several reasons, so we won't use it. We can use machine learning, but it's a bit complicated. You have to fit a lot of parameters, hyperparameters, so it will be too complicated for what we want to do. So we'll use the information theory framework, and especially we'll define the uncertainties on the parameters with the differential entropy. I will explain more in detail what it is later. So the average uncertainty after observing will be the conditional entropy, or more precisely, conditional differential entropy, but it's complicated to say, so I will just say conditional entropy. And so the gain of information I was talking before is just the difference between the differential entropy, the entropy at the beginning when we have no information, no observations, and the conditional entropy, which is the uncertainty after observation. The difference is the mutual information. It's the information we gain with the observation. So the differential entropy is sometimes complicated to visualize. It's just a measure for probability distributions of the variability. So for instance, here we have this distribution, we have 0 bit of information. If we multiply its scale by 2, we have 1 bit of information. It means that to pass from the 1 bit entropy to the 0 bit, we have to divide it by 2. Basically, this is what is doing what is measuring the differential entropy. The fact that if we want to gain 1 bit of information, we have somehow to divide the distribution by a factor 2. And we have things like this. So for instance, here, we have values that are negative. This is quite normal because we can have distributions that are as tight as we want. And so we can go to the minus infinity. We can have bimodal distribution like this. It's not a problem. If the two distributions are really, really tight, the entropy will be really, really negative. And so, as I said before observation, we have the entropy. After observation, in average, we have the conditional entropy. And the difference is the mutual information, which is always positive because observing something can be useless, in which case we have 0 bits of information. But if it's useful, we have a positive gain of information, but cannot have a negative gain of information. At least the observation is unrelated with what we want to estimate, and so we'll have mutual information of 0 independent variables, but never negative, which is quite useful because it's easier to handle than negative differential entropy. Okay, and the mutual information is quite useful. This is the quantitative we will use in the studies because, as I said, it's always positive, but it's also invariant by bijective transformations. And so it means that if you have want to compute the mutual information between AV and a line, you won't have to try different transformations such as the log or the hyperbolic arc sinus or something like this, because it will always give the same mutual information. So you can just give the values as it is without wondering which transformation is good to have something which is basically in a natural scale. So a few questions that astronomers often ask. So how do we compute the statistics? Basically, these are this formula. This is the expectation of the log of the prior distribution of the expectation of the log of the conditional distribution, but it's not really important here because we won't use directly this formula. And of course, the mutual information is just the difference between the two. There are a formula with a double integral, which is a bit complicated. So the definition by the difference is better. Is there a link between the differential entropy and the entropy that we know in thermodynamics? Basically, yes, but it won't go into the scope of this presentation. But there are a lot of links, but also a lot of difference. So it's like you should not interpret the result that I will show after with a thermodynamic point of view, because it will lead to false interpretations. And why it is called entropy? Is it just to make it more complicated? Basically, yes, at the origins, the name entropy has been given by proposed by Richard Feynman, because as the entropy in physics is something complicated that people don't understand well for a lot of people. He said that you calling the value the statistics in the statistics entropy will give always an advantage in the debate. So that's why it's called entropy. There are a lot of similarities, but basically it was merely a joke at the beginning. Okay, so now that we have this, we'll try to, using an ISM simulation, will try to compute the statistical relationship, to quantify it in order to find the most informative lines for different physical parameters. We can do this for observe the map, for instance, in the Orion B dataset. This is something that we have also done, but it's more complicated. The interpretation is more difficult because we don't have an infinite number of data. With ISM simulation, this is easier. We can draw as many samples as we want. And also, this is quite useful for observers because they can predict in advance which lines are useful to observe. And so this is quite interesting, quite different. So I won't explain in detail what is the Meudon PDR code because a lot of people have talked about this before, especially Emmerich. We can draw a lot of precision of a sample in no time with it. So I won't present it at all. To generate our synthetic observation, we will sample parameters theta, such as Pierre and other people have done before. We'll give it to the Meudon PDR emulators and we'll add noise. The noise will be a calibration noise plus a thermal noise, so something quite realistic, in order to have observation that can be observed by an instrument. In our case, it will be the IRAM 30-meter, but it can be any grand telescope as you want. In order to, when we are making an estimation, we'll have a bias and a variance. This is quite important because the bias is a systematic error and the variance is merely the error bounds. So in order to account for it, we can empirically test over a high number of values. We have the bias, we can compute it, and then at the end, with some strategy, we can reduce and even zero it. We can see that the more we have samples, the more our values of mutual informations will be precise with a low bias and a low variance. So that's why using an ISM simulation, which is fast, is really useful because we can take 1 million of samples and we will have quite precise results. So the first result that we'll have here is try to see the influence of the mean signal to noise ratio and the relative integration time. This is a bit the same thing. The relative integration time is with respect to the observation time that we have in the Remy data set at the RM30 meter. So this means that here, 10 at the power 1 is when if we observe 10 times longer, what do we get? So for instance, here I will focus on the integration time, which is more interesting for me. Here it means that if we continue for HCO plus to observe, we observe 10 times more, we'll have the same values of mutual informations between the physical parameters and the line. So it means that it doesn't matter to observe more. The lines are already a good signal to noise ratio. But if we observe less, we'll begin to fall here, and so this is not a good thing. But for the other lines, we can observe more and we'll gain mutual information. So for an observer, this is a good information. If we want to use those two lines, we should observe more. But in the case of this line, this is not important. Also, this can lead for the writing of proposal, for instance. Another thing we can do is to do the analysis for a single, for a given physical regime. So for instance, here in translucent gas, we have the ranking of the most informative lines for AV. So this is a quite simple case. So we have the 13CO, HCO+, so lines that we know that are quite related with AV. And we can do the same thing for combination of two lines. This is interesting in this case because this is something that we cannot do with Pearson correlation coefficient, for instance. And so here we see basically that the most informative lines, a combination of lines or combination of the most informative individual lines. So this is not quite surprising, but this is not always the case. For instance, here we have 12CO, lines of 12CO, which is not individually very informative. And when we combine it with other lines, we have a couple of lines which is very informative. And so these are this kind of conclusions that are important if we want to derive information in translucent gas with 12CO. We have to combine it with other lines, and those lines can be given by this kind of analysis. We can have this kind of maps, which is the same thing as that, but for two physical parameters, AV in the x-axis and G0 in the y-axis. And so we can have the dependencies for two physical regimes. So what we can see here is that 13CO is really informative on AV, but for physical regimes that are in this kind of regions, so like medium AV, and it doesn't really matter the value of G0. For other lines, for HCO plus here, we can see that the informativity of HCO plus is just in this corner of the space of the space of the parameters, and we can do the analysis for other lines. So 12CO, this is only for low AV, something that we know, but we can quantify it for the different physical regime. We have a dependency in G0 too. We can also do this for combination of lines. We can do this for G0. We have completely different graph here. We have the H and C is informative on G0 only in this region of the parameter space that have some properties that are not much in other place. And we have that 12CO is informative on G0 for a large part of the space, and it doesn't really matter the value of G0 and AV. And to terminate it, there is some result that I really appreciate is this one. So we have the information maps for this C18O lines, the second transition. We have the maximum for pixel-wise maximum for the two maps, and the combination. And we can see that the two maps are different, which means that when we combine the two lines of C18O, we have really more information that if we just take the most informative lines. The difference is this map, this is a combination gain. And we can see that for some regions of the parameter space, we double the informations that we have when we combine the two lines instead of just taking the most informative one. This is not completely new, but we are able to quantify the influence of this combination. And so if it's worth or not to observe those two lines, if it can be complicated, we know we are able to quantify the gain of doing this. But you can do this for other lines. So for instance, 13CO and C18O. And the same way, we have a combination which is different from the pixel-wise maximum. And so in this region of the parameter space, we have a combination, an information gain, which is high. And this is quite interesting because it was a region where the two lines were not really informative individually, but when we combine them, we gain information on a region where they were not previously informative. And this is a really interesting result, actually. Okay, I will go fast on it. At the beginning, we have to sample the physical parameters. The problem is that there are a lot of ways to sample the parameters. This is a kind of prior distributions. We can use a uniform distribution or another distribution, for instance, an empirical one. There is no good way to do this. The only difference is that it depends on what you want. In this case, you will have something that is close to the reality, for instance. For this one, you will assume that all the parameters are equiprobable in the nature. There is no good way. You just have to do to choose the way to sample in order to answer the very questions you're asking. And we can do this also for data, not for simulations. And here, this is a different figure. It indicates for different physical regimes the most informative couple of lines with a probability that this couple of lines is really the most informative using the error bars. And so we can see that for the different physical regimes, using the maps, we are able to have the most informative lines. So here we have the famous couple 13CO and 12CO, but for other parts of the physical parameter space, we have other lines N2H plus for dense region with low AV, low G naught. And for dense region with high G naught, we have SO that appears as a good candidate for same for CS, etc. I will pass this one because I think I know really time for that. I wanted to talk about something which is completely different after that, also based on information theory, which is another use case when information theory is useful, is for the denoising of PPV cubes. So I won't go into the detail of the denoising, but I'll just present where the mutual information is useful in order to have a better denoising. So in our case, we have this kind of maps, of velocity maps. So this one has a pretty good signal to noise ratio. In this case, it's more complicated, and for this one, it's really complicated to distinguish the signal and the noise. And so for this kind of velocity channel that we really need a denoising method. So the denoising method, we already have a talk yesterday about this. We have 3D data that we want to denoise. We want it to be unsupervised because we don't have run truths, basically. And we have no spatial informations for the verification, so we have to find other ways to check for denoising. And the constraint, we don't want creation, loss, or distortion of hallucinations. We want to be sure of what we get at the end. So the methods to do this is what we call an autoencoder neural networks. Basically, this is just a neural network that takes line profile at the beginning, that will try to encode it in a lower dimensional space and will reconstruct it. And because of the dimension reductions, we will have a signal which has been denoised the same way that if you have several values with noise, you can just compute the average values and the noise will decrease with a factor square root of n, where n is the number of samples. This is the same kind of things here. The lower is the bottleneck, the low dimensional space, the better the denoising will be. So this is a method which is really used, often used in the hyperspectral signal processing community. So at the beginning of my PhD thesis, I tried this one, and we have a problem in astrophysics. It's that it's not that simple. Okay, so when we want to compute the mutual, if we want to be able to encode signals in a lower dimensional space, you have to exploit redundancy. Redundancy means that there are informations between the different velocity channels. In our case, this is not always the same. We have information between the channels, information which is not always linear. So this is a mutual information maps. We can see, for instance, here, those velocity channels have a lot of information in common with this one, but it's not always the case for all the velocity channels. But what is important is this figure. It means that, so we have in x-axis the velocity gap, the velocity gap, the distance in the velocity axis between two velocity channels, and here the average mutual information. And we see that the more distant are the velocity channels, the lower is the mutual information, which means that if we want to encode together velocity channels, they have to be really close velocity channels on the velocity axis. And if they are really far apart, it will become impossible because the mutual information will tend to zero. So in the case of our astronomical data, it's not possible to encode together all the velocity channels. We are just able to encode together channels that are close to each other. So we are not able to match these conditions, which is basically at the core of all the algorithm in the hyperspectral community, which is that the intrinsic dimensions, the size of the lower dimensional space, has to be really lower than the intrinsic dimension. And if we don't match this property, we cannot use all the algorithms that are really useful and really performant for terrestrial hyperspectral data. And so in order to do that, we completely changed the architecture of the neural networks in order to be able to encode only the channels that are close to each other. Doing that, we are not able to encode in a really low dimensional space the signal, but we are able to encode only the channels that can be encoded together. And so at the end, we obtain something which is without hallucinations, with better results than what we had before, where we try to encode together channels that cannot be encoded together. And this is an important conclusion because this is a property which is quite specific to astronomical data. I bet that for all hyperspectral data that are managed in the hyperspectral community, this is some property which is verified, and this is not the case here in astrophysics. We have to set up our own set of algorithms which are based on specific properties of our signal. Okay, and so at the end we obtain this kind of results. So I don't know if the figure is clear, bright enough to see the difference. We have the raw data, the denoise data, and the residues of these velocity channels at the end. So we can see that there are not a lot of signals. Sometimes we have like block in the residues, and they are really related with the way the data are observed, with correlations between the noise due to the movement of the telescopes during the observation. So this is quite normal. This is a good result. Okay, so in these presentations, I introduced the information theory as a good framework in order to define and capture and quantify the statistical relationships between some variables, and especially between physical parameters and line observations. So I introduced the entropy and the mutual information as statistics that are able to capture it. And I insist on the fact that this approach can be used in astrophysics, but can be used, and it is used actually, in other domains. It can go from other branch of physics to human science. And using this framework, we propose an approach based on simulation in order to quantify to which extent an observation is able to constrain physical parameters. And this approach is able to account for instrument properties, calibration noise, thermal noise, the observing conditions, and the integration time, which is really useful for observers in order to compute, to predict the time that is useful for the observations. And it can be a way to justify the choice of observing times in the proposals. Okay, and so all this work, including the approximation of the Meudon PDR code, the library, the Python library, InfoVar, that is able to compute all these the mutual information and the entropy. The library that is able to produce all the figures that you have seen, the maps and the bar plots for the ISM observations. They are all in a GitHub repository, which is free. You're free to use it, to contribute if you want. And all the figures that I've shown are also reproducible in the GitHub repository, or the figure of the article. So you can try your own, change the setup in order to use it for your own use case. And so I think I'm done. So thank you for your attention.
Thank you, Luca, for your very nice talk. We have maybe time for one small question.
Thanks. Very interesting. Let's see if I understood correctly. So your denoising algorithm is basically sensitive to high frequency noise in the frequency axis, right? So you said that the closer pixels in this frequency space is what you can encode, if I understood correctly.
I'm not sure. I'm not sure I will say it like that. I'm not sure that the high frequency noise is really a problem, but maybe I don't.
No, that the one that you can remove. This is your denoising part, right? So if you go to when you have these three images, the raw, the denoise, and the residual, the residual is basically a high frequency noise.
Yes, of course. Yeah.
So
you're right.
my question is, can you also, or how the algorithm deals with correlated noise, correlated spatially noise, because there are instruments that produce this, not only by the pattern of observation, but for instance, interferometers, that produce this type of noise. How does it work? Because there's a very interesting approach for that.
It's a good question. Actually, in the paper, there are a large part of the study of the noise, because the property of the noise of this kind of instrument is really complicated, with special spectral correlations, the influence of the beam. So actually, we are not able in the neural networks to take it as a consideration, because we don't use spatial information. This is something that I didn't say. But when we check the result, we don't have ground truth, but we can check the properties of the noise. And so there we have a good noise models, and we can compare the residues to the properties of this noise with spatial correlations, spectral correlations. So we are not able to use these properties for the denoising, but we are able to use them in order to check whether the denoising is good or not.
Mm-hmm. Oh, very, very interesting. Yeah. Thank you.
Thank you for the talk. I'm not a specialist on data processing, but I was a bit surprised by some of your results when you show the impact of the double couples of results, and specifically, yes, this transparency, no, the other one, yes, this one, when you show that the N2H plus combined with C18O could be a good partner for checking the radiation field, because N2H plus is a tracer of dense gas. So that's my question.
Actually, that's a very good question. The reason why the result with the ISM simulations has been easier to publish is because the results are maybe less surprising. In the case of the Orion B data, we have two things. Some results that are quite surprising, like this one, and the interpretation is more difficult. So I don't have a physical answer. I don't have the.
I think this is related to the fact that we have line of sight in the Orion B data, for which we have only one value of G naught. Okay, and we still have a dense core, and so we still see N2H plus. This is related to what Leontine showed yesterday. So on the line of sight, we have more than one regime. So this needs to.
It's not really physical.
Well, what is physical? What is physical is that in nature, when we're looking at a dense core that is illuminated from the outside, you will always get this situation. Okay? So always. From the Orion B viewpoint. So it's when you're as an observer, this is a useful information. As a modeler, maybe not.
Just I think this is a combination of two lines. We can see that here, for instance, the probability is a bit low, so we are not sure of which line is the most informative. And this is a combination of two lines. If we are just taking into considerations for a lot of cases, single lines, there are some lines that are in the best couple, which does not appear as a good candidate for individual lines. So this is not quite surprising for me that tracers of dense gas and tracers of thin gas are combined together, because they are maybe information that can bring to each other. But the line, as you said, is not a good tracer for when we take it individually, just as a combination here. Another line, which is a good tracer individually.